This video continues the idea of some stats theory application. So based on the central limit theorem, if the sampling distribution is going to follow a normal curve, now we can talk about whether a study's result, a specific study's result, is expected or unexpected. So let's start with the idea of a coin flip. I know that you've all done this before. If we tossed a coin 20 times, the probability of heads is 1 in 2. The probability of tails is 1 in 2. So it's a 0.5 for each one. We're expecting to flip the coin 20 times and get 10 heads and 10 tails. Does that mean we're going to actually get 10 heads and 10 tails? Has any of you ever done that and had it be perfect? No. So you're telling me that our actual results don't match the predicted probability. That sounds like a problem to me. Let's look at it. So if we take a sample, so we do this the first time, trials is also called. I get 16 heads and 4 tails. That is nowhere near the 10 and 10 that is expected. But this is only one sample. This is like having one person represent the entire, one teacher represent the entire population of teachers. That doesn't make any sense. So we do different samples, we do different trials. So here we have 15 different trials, 15 different samples, and these were all just complete random. And here I have 9 heads and about 11 tails. So that's much closer to our 10 and 10 that we're expecting. In fact, if I increase that from 15 to a sample size of 30, I'm now much closer to the 10 and 10 that's expected. Even more so if I increase to a sample of 100. I'm almost exactly at the 10 and 10 that is expected. But I can look at a specific trial and see how that trial compares to the rest of them. In this case, we have 2 heads and 18 tails. That is unexpected. That's not what we would expect. So something different is happening in that trial. So is it possible to flip a coin 20 times and get tails each time? It is possible, but it is not probable. So statistics is the study of uncertainty. It's all about how certain do you want to be. Are you okay with 80% confident? Do you want to be 95, 99% confident? If you're in a medical study, you better be 99% confident and only allowing 1% uncertainty, error. We never actually have a probability of 0 or 1. But we can get really, really close to 0, we can get really, really close to 1. If it was a true 0, that would mean that there's no rabbits in the deck of cards. Why are we looking for rabbits? And a 1 would mean the entire deck of cards is kings. In that case, it's a fact, and we're not talking about probability. Probabilities have their own distributions. The heads and tails example would look just like that, where we have an equal probability of heads and tails. For this one dice, the probability is flat, the distribution is flat, it's not that curve. It's a uniform distribution. There's equal probabilities for each outcome. We had 2 dice, that's not the same. There's actually more chance of getting a 7 because there are physically more combinations that would equal a 7, which is why you don't make any money at the casinos if you roll a 7. You make money if you roll sneak eyes. There's only one opportunity, one combination of all of these that would result in a 2, and the same for a 12. So we have a very different distribution. In fact, that looks like a normal distribution, which leads us to the idea of probability theory distribution. Here we're looking at the distribution of potential outcomes. So 68% of trials of samples are going to be right here. Some of them are going to have a little bit more heads, some of them are going to have a little bit more tails, but they're going to be right in that 10 to 10 expected outcome. Some of them, like the example we looked at, are going to have a lot more tails and not as many heads. That is an unexpected outcome, and those are going to be on the tails over here. So if I flip a coin 50 times, it is possible they all land heads up. But that's going to be an unexpected result, and it's going to be way over here. The chance of that happening is really, really low. We have what we expect over here in the middle. So let's apply that to an actual study, which is where we're going with all of this. If I'm curious if there is a difference between guys and girls scores on, let's say, math anxiety, the null hypothesis is going to say that there is no difference between guys and girls. They have the same amount of anxiety. The alternative hypothesis is that the groups are going to be different. So I'm going to conduct a t-test, and that is going to give me a result. If that result falls in this gray area, that means there's a high probability that the null hypothesis is true and that there is no difference between guys and girls. If my study score, if that t-test, if that value falls on one of these tails, there's actually a low probability that the null hypothesis is true, which means I just found evidence of an unexpected result that is giving me the idea that guys and girls are different. So I'm going to reject the null, and I'm going to say that my finding is that guys and girls are different. So I want you to keep this in mind as we continue moving into hypothesis testing. And if you need to watch these videos again, that's totally normal.